Okay, so we ended last time talking about the singular value decomposition and establishing that a singular value decomposition actually exists, right? So we said that if I have some matrix A, I can always write it as this U sigma and V transpose, where if A is m by n, U is m by m square, V is n by n square, U and V are both orthonormal, and sigma is m by n, always the same dimension as A, and it is almost diagonal, which means that basically if A is tall, then it has kind of a diagonal matrix at the top and a bunch of zeros at the bottom. If A is wide, then it has a diagonal matrix kind of at the front and then a bunch of zeros after. Question?
What's the relationship between that form and like spectral theorem?
The spectral theorem only applies. The question is, how is this related to the spectral theorem? The spectral theorem only applies to symmetric matrices. This applies to every single matrix you will ever meet. Symmetric matrices are a very, very, very special kind of thing. You won't you see them, but they're rare. Okay? So you use the spectral theorem to prove that the SVD exists, right? How do we find the SVD? The SVD is based on the eigenvalues of A transpose A or A transpose, right? There's two ways to compute the SVD. Last time we did it by looking at the eigenvalues of A transpose A. Alternatively, you could do the exact same procedure by looking at the eigenvalues of A transpose. The eigenvectors of A transpose correspond to U. The eigenvectors of A transpose A correspond to V. A quick dimensional analysis will let you figure out which corresponds to which. You use the eigenvectors and eigenvalues of that symmetric matrix A transpose A or A transpose to be able to compute U sigma and V transpose. So this is it's related to the spectral theorem, but it's totally different. Okay? We also talked about the compact SVD form, where you could instead write this as an m by r matrix, a square r by r matrix, and then an r by n matrix. There's another way in which you can write the SVD, and you can write it basically as a sum sigma I ui vi transpose. So UIs are the columns of U, VIs are the columns of V. I always write V's with this little circle here and U's with this little tail here, right? U's and V's can look similar, but my U's will always have a tail, my V's will always have a bubble. Okay? So if I have R non-zero singular values, I can write this in this particular following form. This is called the outer product form. What is the dimension of UI VI transpose? Right? Is this a scalar? No, right? Is this a dot product? No, this is not an inner product, this is an outer product, right? So this is going to give me a set of m by n matrices that I add up to get my A. The convention with the SVD is always to order your singular values such that sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma r, and sigma r is always greater than 0 because you always assume that you have r, if r is the rank, you have r strictly greater than 0 singular values, and then sigma r plus 1 all the way up to sigma n is 0, right? Whichever one is bigger, right? So all the remaining singular values are assumed to be 0. U is an orthonormal matrix. What does that mean about its invertibility? Good. So you answered your own question. Good. V is also an orthonormal matrix. What does that mean about its invertibility? Now what we want to go from here is I want to teach you a different application of the singular value decomposition. And particularly, I want to teach you what it means to have a low rank approximation of a matrix. This is an application that is particularly useful for data compression. And if I have time, I'll show you a demo of how this can work. It's It's very connected to principal components analysis. And again, it's about pulling out what is relevant and what is most important from the data. But to do this, I want to first introduce to you the idea of matrix norms. This is something that we will use in the context of compression in the example today, but it's something that comes up just more generally in many optimization kind of settings, right? So when I think of a matrix I can think of in many different ways, right? One sense, a matrix is basically like a vector, but it's in 2 dimensions, right? Instead of just having a column vector like this, I also have things going along the rows, okay? And so one perspective when you think about a matrix is to think about the matrix as a block of data. Right? And when I think about that, last class we were looking at images, and we had kind of a bunch of pixels, right? I have a 64 pixel image, an 8 by 8 image. I can think of that as a matrix, right? Every value of every one of those pixels I can put into a matrix, and that's kind of my block of data. But when we were doing the example last time, we didn't actually think about that matrix or that image as a block of as a matrix, right? We thought about it as a vector. In fact, what we did was we unrolled it to make a 64 length vector, right? So in that particular case, while we could have thought of it as a block of data, we did not. But there might be many different ways in which you might want to think about a matrix as a block of data. And if you're thinking about the matrix as a block of data, the relevant norm is called the Frobenius norm. And it's basically saying the Frobenius norm of A. Again, I've now represented Frobenius by this F right here, is the square root of the sum of the squares of all of the entries. I will go from 1 to n. J will go from 1 to m. Let's say A. So I'm basically doing exactly what I would do for the norm of a vector. What do I do to find the 2 norm of a vector? I take the squares of all of the elements, add them up, and then take a square root, right? The Frobenius norm is doing exactly this for a matrix. So in that sense, it's really treating the matrix as a vector, right? It's doing that same thing that you would do to compute the norm of a vector, but in this case, for the entries of a matrix. There's now a much easier way actually to compute the Frobenius norm, and this is the way that it is often computed. It is a trace of A transpose A. So the trace, just as a reminder, is the sum of the entries along the diagonal of a matrix. And an important property of trace, which you have possibly seen before, but possibly not, trace AB is equal to trace BA, assuming A and B commute. Okay? So it's only in the case that these two actually commute. How do you show that this is actually equal? How do you show this part? Just a reminder, trace equal to sum . So how can I compute this quantity? Yeah.
Go by each row, like column, like each diagonal.
So let me think of my matrix A. Is that correct with what I said? Yes. Okay? And then A transpose has basically the transpose of this, right? So when I think about A transpose A, what is my first entry of A transpose A? Here, in this matrix. Remember, what is A transpose? What is the first entry up here of A transpose A? I take the first row and I dot product it with the first column, right? So here I get So I'm noticing a lot of you are waiting for me to write the answer on the board and then taking notes. It will be helpful for you if you try to write the answer on your own when I'm having these small pauses in lecture. Try. You might get the wrong answer. You might do it wrong. I won't always have time every time to give you like a 1 minute to think through the thing. But the more actively you're engaged in lecture, the easier everything else will be. So just a tip. So here we have A1 transpose A1, right? We're interested in the trace of this thing, so what's the next element of interest that we want to compute? Right? So what is this entry going to be? A2 transpose A2, right? And what is A1 transpose A1? It's the 2 norm squared of A1, right? This is the 2 norm squared of A2. What am I going to get? 2 norm squared of AN, all the way at the bottom, right? And is that exactly equal to this? Right? So do you see how these two are equal? Okay? So when in doubt, just doing a simple calculation, a simple example, is often a very good way to kind of remember how to do something or confirm to yourself that you believe something is true. Okay, so an important property of the Frobenius norm. So on your homework this week, last week, you proved a property of orthonormal matrices. What was that property of orthonormal matrices? They don't change the norm of a vector, right? You proved that on homework, you proved that if U is an orthonormal matrix, X is a vector, then the 2 norm of Ux is equal to the 2 norm of X, right? Orthonormal matrices will only rotate or reflect. They will never change the norm. They will never scale, right? That's kind of the fundamental thing of the SVD. The SVD says U will first do some kind of rotation reflection. Sigma will, all of the scaling is captured in that sigma, and then V will do another rotation or a reflection, right? So this is an important property. What I'm saying here is that the same thing holds true for the Frobenius norm. Right? Orthonormal transformations of a matrix will also not change the Frobenius norm of a matrix, i.e. how much the matrix scales something, right? Sorry, not how much the matrix scales something, that's the spectral norm, which we'll come to, but it won't change the, basically, sum of the squares of the entries. So how do you prove this? Okay, I'll give you a minute to do it out. So let's do this out. So what is the Frobenius norm of, how do you want to write this? What's the convenient way? Just speak up loudly. This is the trace of UA transpose, which I can just write as, now we've done this enough, transposing. Did I do that correctly? Yes, I did. Okay, good. What do I get? What is a nice property of orthonormal matrices? Their identity. So this is equal to the Frobenius norm of A. What if I had AU Frobenius norm? This is equal to the trace of, now what do I get? I get U transpose, A transpose, AU. Now what do I do? SVD of? Okay, SVD could help me. How would it help me? U is not necessarily connected to the SVD. U is just any arbitrary orthonormal matrix. Can we use the trace property? Yes. What trace property do you want to use? The commute, right? So what are you going to do? I'm going to pull this U over to the other side, right? So this is equal to square root trace of U transpose, A transpose A. And now what you get is therefore square root of, again, basically this now gives you immediately that this is the identity. This is equal to the Frobenius norm of A. One of the reasons I like working with the full SVD I was telling you last time is then that the U and the V are all square orthonormal matrices, right? And square orthonormal matrices means that U transpose is equal to U transpose U, and both are equal to identity. When you have non-square orthonormal matrices, if you have a tall matrix that's orthonormal, this property will not hold, right? Only one direction can you get an identity. The other direction you will not get an identity. So you always have to keep track of that when you're dealing with non-square orthonormal matrices which show up in the compact SVD. And it's just much easier to always be able to say U transpose is identity. So that's one of the reasons I prefer the full SVD when I'm working with it. Good. Any questions about this? We're good? Okay. Moving on. Second matrix norm. So we talked about this matrix as a hunk of data, but what's the other way in which we think about matrices, or that matrices are useful to us? What's the other standard thing that we want to do with matrices? Yeah? They're transformations, right? Matrices are operators. And so when we want to think about a norm of a matrix, maybe we want to think about it, how that matrix behaves kind of as a function, as an operator. Okay? So this second norm, which is called the spectral norm, sometimes the L2 norm, thinks about what the matrix is doing when it is operating. So if I think about the L2 norm, or the spectral norm, and the name that we're calling it the spectral norm, which kind of suggests something is coming, right? You might get a hint as to where we're going, so let's see. This is saying what happens when this matrix operates on a vector. Okay, so it's saying consider some vector x and consider what happens when A acts on it, right? It's taking it from one vector space into another vector space. And the question is, how much can this matrix scale this x? I'm not cared about rotations and reflections, but I'm cared about, is this matrix going to scale it by 100? Is it going to shrink it by 10? What's going to happen? So the max scaling that you can get of a unit norm vector is called the 2 norm, or the spectral norm. So it's important to notice here, on the left-hand side, there's a notation that looks very much similar to the notation on the right-hand side. But these are two very different objects. On the left is a matrix norm. On the right is a vector norm, right? Because AX is now a vector. So this is a repeated confusion that I see happening in students. Make sure you know what the object you're taking the norm of is, okay? But now, can I simplify this further? Do I know how to compute this thing? If I want to compute the 2 norm of this vector, how could I compute it? Well, how do we always simplify this thing as? Very good. So I always say, when I have the 2 norm, I can always write this as AX transpose AX, right? And now I have to take the square root, right? Which is equal to the max And now what is this thing? Have we seen this thing before? Yes? What is it? Rayleigh coefficient, right? What is the value of this thing? Do we know it exactly? Exactly. This is lambda max of A transpose A, but now we have another way of writing this even more compactly, which is sigma max, or sigma 1 of A. Right? It's the largest singular value of A. So you can see why now this is called the spectral norm, right? What it's saying is that the spectral norm of the matrix is what is the maximum scaling it can inflict on the vector. Okay? It will never scale your vector by more than this. And the only vector that it will scale as exactly as this much is something that is exactly aligned to the largest eigenvector of A transpose A, right? Or the first singular vector. So the question is, how is this connected to the determinant? Is that like
Yeah.
So you all, discussion 1, I think, you have proved something about the determinant and the eigenvalues. Did you prove this in your first discussion? What did you prove? The determinant is the product of the eigenvalues, right? So basically, the determinant is capturing, in a sense, the scaling as well.
It's just not the max scaling.
It's not the max scaling. It's now the product of the eigenvalues. So there's different notions in which you can characterize the scaling. This is the max scaling, right? Now that you're thinking about these max scalings, what do you think should happen if you take an orthonormal transformation of a matrix? Is the max scaling going to change? Probably not, right? So what's the theorem you want to write down? What do you want to be able to say?
The same as the theorem in the Frobenius constant. Replace half with 2.
Yeah. The 2 norm is equal to the 2 norm is equal to the 2 norm of A. If U is ortho. Okay, again, take a minute and prove this. Okay, that's my timer. So how many people are done? Okay, which one are you done with? Both of them? One is easier than the other. Which one's easier? Which was the easier one to start with? First one's the easier one, right? What happens when you do the first one? It's kind of exactly like this. The U transpose U's cancel, and you get an identity, and it just kind of trivially falls out if you just write out the definition, right? The first one's easier. Everyone sees that? So let's do the second one together. Everyone with me? I'm worried that I know that I got this section of the class. What about that section of the class? You folks with me? Okay, good. So how do I do this? What do I do with AUX? What is the 2 norm of AUX? How can I write this? This is the max of this. So if I further write this out, this is the max. And then everyone hopefully wrote this step, which is X transpose, U transpose. What do I want to write? I want to write X transpose, U transpose, A transpose, A, U, X, right? This is what we got. Now these U transpose U's are not canceling, right? Is there a trace in here? No, right? There's no we can't do what we did here and just kind of move the U's around till they cancel each other. So what are we going to do? What's the thing that you want to try and do here? This is a trick that we've used before. In last week or sometime? Yeah, at the back. Substitute UX with a new vector. Great idea. So if I take UX and I call it Y. Okay? What do I know about Y?
That's the same norm as X.
Y has the same norm as X. So if X is a unit vector, what must Y be? Unit vector, right? So can I now rewrite this optimization problem as a maximization over Y the norm of Y is the same as the norm of X, but now I have this thing. When I write the definition of the 2 norm, does it matter if I call this variable gamma or gobbledygook or X or whatever else? Doesn't, right? It's just a dummy variable that I'm optimizing over. So is this thing exactly equal to this thing? Right? So therefore, this is again equal to the 2 norm of A. Everyone with me? Thumbs up at the back? Yes? No? Yeah? Good. Okay, excellent. Wonderful. So now that we have all of the preliminary stuff, we can move on. So what we're going to try and do now is we're going to say, let's say I have some matrix A. Okay? And let's say this matrix is rank R. And let's say A has an SVD. Okay? What I want to try and do is I want to say, look, large rank matrices means that there's a large number of basis vectors and their coefficients that I have to keep a track of, right? Basically, if I take the SVD and I have a large rank, that means that there's many, many singular values that are not 0. A low rank matrix has most singular values equal to 0, right? The rank of the matrix is the number of non-zero singular values. Everyone see that? So if I wanted to just store my matrix by just storing the singular values, for example, low rank matrices are easier to store, right? Make sense? Can I approximate my matrix by a low rank matrix? Can I say that, instead of having this rank 1000 matrix, I want to have my matrix be only rank 10? How much am I losing? How much am I losing in a Frobenius norm sense? How much am I losing in a 2 norm sense, right? If I'm thinking about my matrix as an operator, does it really, if I zero out some of my components, does it really affect how the scaling of the vector is going to happen? If I'm doing this in some very large dimension and I'm only caring about approximate results, can I do this, right? Engineers, mathematicians, computer scientists, the name of the game is trying to do more with less, right? So if I can do something with less data or get it approximately right, it's always in my interest to do this, okay? So that's kind of what this low rank approximation is trying to get at. And so what we want to think about is first, I want to find, maybe I want to say argmin. I want to find the matrix B okay, such that B belongs to R m by n. It's the same size as A, but the rank of B is at most K. So I want to find a rank K matrix that is approximately equal to A in the 2 norm sense, right? When I take the difference between A and B, and I take the 2 norm of that, I want that to be small. Okay, that's one way to think about this. And the second thing I want to compute is the argmin. B, again, belongs to R m by n. Rank B, again, I want to be less than or equal to K. But now I want to look at A and B in the Frobenius norm sense. So now I'm looking at how does every individual entry of this matrix B differ from A, right? And I'm taking the 2 norm of all of that. So they're looking at the difference between A and B in 2 different perspectives. One is looking at kind of what is the residual, or what is the difference between how A and B operate on a vector. And the other is looking at how do A and B look different as chunks of data, right? These are the 2 different kinds of comparisons we're trying to do between A and B. Does that make sense to everyone? Turns out, by sheer crazy magic, does not happen in real life usually, the answer to both of these optimization problems is exactly the same. Which is really shocking, right? Because a matrix as an operator and a matrix as a chunk of data are 2 very different interpretations of a matrix. There's no reason for these to be naturally kind of aligned to each other. Second thing is, what is this equal to? Well, I'm going to define AK, which is the sum I equal to 1 to K, sigma I, Ui, Vi transpose. So basically, take the SVD of A. So I can also write this as sum is going from 1 to R, sigma I, Ui, Vi transpose. So basically, the answer is pretend that a bunch of the singular values are 0. And which ones do you set to 0? The smallest ones. Keep the largest K singular values, and that's your best approximation. That's what this AK is. Turns out this is equal to AK, and this is equal to AK. Yes, so if you were thinking about the principal components, so the question is, how is this similar to PCA? So this is similar to PCA in many ways, but PCA is solving a distinct problem which also happens to have the same answer. PCA is saying, can you give me a projection onto a particular lower dimensional subspace such that individually each of my data points is close?
So PCA solves all three of these?
PCA does not solve all three of these. All three of these are solved in a sense by the SVD. And these are three different interpretations of the SVD. There are three different optimization problems that by crazy magic happen to have the same solution, okay? And we are basically going to prove that these all have the same solution, okay? It's not obvious, but if you just ask these questions, you know, how should I project my matrix so that I get the smallest distortion? There's no projection happening here, right? These are all different questions, and what we're going to do is prove that they all have the same answer, okay? So the question is, how can we prove that the norms are related to the information content in the matrix? So this is a question that basically comes down to, why do you care about this loss function, right? And partly, it really depends on your application and your implementation. And so it turns out that this particular interpretation can be helpful for data compression, right? When you think about this from the Frobenius norm perspective, that is really saying, like, if I think about my matrix as an image, right? It's just representing a bunch of pixels. How much can I tweak the individual pixels values by? And how can I make sure that that difference is as minimum as possible while getting the maximum savings in terms of compression? Right? So information content is in the eye of the beholder, right? What information is useful to who depends on what you're going to do with it. So compact SVD will always have R non-zero singular values, right? We're not choosing that R. That R is a fixed function of A, right? What we're saying is that instead of trying to have R singular values, can we get away with fewer? And so maybe I should do this demo first. Maybe that will kind of get... I was going to do it afterwards, but I think maybe it's worth doing it now. So let's look at this. So let's say I have this image, right? Cute, right? And what I want to do is I want to store this image. And I have this image, and what are the dimensions of this image? Okay, it's a 900 by 1200 matrix, right? So a lot of data in this image for this matrix to look this cute. And here I'm really thinking about this matrix as kind of representing this as data, right? What I care about is how cute the kitten looks, right? That's kind of our metric of evaluation. And now what I'm going to do is I'm going to take the SVD of my kitten matrix, and I'm going to pick the top k singular values, okay? So now, how many singular values do I expect for this, right? Assuming this is close to full rank, there might be like 900 singular values. But let's say we pick the top 200. I can basically, this is just, I'm just picking out the top 200 singular values here. There's nothing really happening in the code. And if I just now plot this, with that only 200 singular values, this is the kitten that I get. This is the uncompressed image on the right? And visually, it's extremely hard to tell the difference between the two images, right? I'm looking at it close on my computer. You guys are looking at it on this giant screen. And it's still like, if I didn't put the titles on this, it would be kind of hard to guess which one was the uncompressed version and which one was the compressed version, right? So as you can see, especially when you're dealing with data-intensive applications, compression can bring you a lot of bang for the buck, right? Netflix doesn't want to stream the same thing to you if you're streaming onto your phone versus if you're screening onto your giant high-resolution HDMI television at home, right? It's not worth it. It wouldn't be efficient engineering to do that. So how do you figure out what to stream when, how much resolution do you need, right? These are the kinds of techniques. This is just one compression technique. You can take 3 graduate courses on compression and get your PhD in it. Like there's a lot to do here, but this is just one example. So the question is, how do we choose this value of k? And so now what I'm doing is I'm plotting the singular values of this matrix, of this kitten. And if I just plot them, I can see that basically there's this giant singular value here, and then they're all dropping off really, really fast, right? They're getting very close to 0. It's kind of hard to see, like exponential curves are sometimes hard to see. So now if I plot them on a log scale, so instead of plotting sigma, I'm plotting log of sigma. And they're kind of, you can still see how they're dropping off. They're starting at 10 to the 5, 10 to the 4, 10 to the 3, 10 to the 2, 10 to the 1, and then they're going off to 0. And so there's like quite a bit of spread between these different singular values. And so this can give you a hint of like, if you had to pick which are the most important ones, you want to pick the heavier ones first, right? And so if I have this now, I can basically, this really nice plot that one of my students made, former TA, Daniel. Let's say I could move this slider. I hope this works. Please work. Good, you work. So if I keep 0 singular values, right? What does it mean to keep 0 singular values? I've set every singular value to 0. What is this AK equal to? 0, right? When AK is 0, I get a completely black screen. Okay? Now if I change this a little bit, let's say I make AK 10. Takes a little bit of time to run. With 10 singular values, my kitten is getting there, but not as cute, right? It takes a while to compute. But like, you can still tell it's a kitten with only the top 10 singular values, right? I'm using less than 2% of the data total. And still so much of the structure has been preserved, right? And so if you're displaying this as a tiny thumbnail on like a tiny little screen, maybe this is all you want to send, right? But now as I increase this, my resolution's kind of filling in. Right now I'm going up to 56. Even at 56, like my background is blurry, but look at how clear the eyes are. I mean, it's remarkable, right? Somehow this SVD is really just pulling out what is the most important stuff. And you get the idea, right, of what this is trying to do. So as I keep going and going, of course, I will, keep increasing the resolution. But I think you all get the point, right, of what we're trying to do and why this is interesting and important. Questions about this demo before I shut it down? Yes, question at the back. So how do the distributions of the singular values differ? It's a good question. So I'll show you one more thing. So here's another image, right? It's a much more structured image. And so you might imagine that for this image, the singular value drop-off is actually sharper. Because there's more structure, you need fewer things to capture kind of the structure in the image. And so you can see this actually, is that for this, again, I have, like if I just plot on the linear scale, I see the same kind of exponential drop-off. But now when I take the log of sigma versus, am I plotting the right thing? Yeah, if I plot this on the log scale, this drop-off is now much sharper, right? It's going to 0 far faster than the kitten did, right? And that's because that there's more structure in that image, okay? And again, here you can like kind of do the same thing and recover this image with. It'll take a minute for this demo to load, but you can do the same thing and you can use far fewer singular values to recover this image to pretty good resolution because there's so much structure in it. So the compressibility of anything is, to some extent, a function of how many patterns are in the data and how well can you recognize them, and therefore encode them compactly. Yes?
Generally, those structures have to be like linear as they are here. Like if you had
No, they don't. They don't. I mean, there can be different kinds of structures, and one of the things that you can do is you can do different kinds of transformations to identify features that can make it easy to compress. That's a whole other different kind of thing. Yeah.
Which of these two nodes that dominate how the picture looks like?
Which of these two what?
Nodes, like matrix nodes.
matrix norms.
Like,
I'm not sure I understand the question. Which of these two matrix norms dominate how the picture is going to look like?
yeah, I mean, like, so we want like try to minimize those two nodes, and we want to make the picture like with less trace.
I mean, when we're thinking about this matrix as a picture, we're really thinking about it in the Frobenius norm sense, because basically the individual pixel and the difference in it changes how we visualize it, right? So here, in the case of the matrix, we're really thinking about the Frobenius norm. And in case of the image compression, we're really thinking about the Frobenius norm. Yeah. Yes? I mean, yes and no. I'm not sure what you entirely mean by that, but basically, these are different lenses for looking at the same thing, right? Fundamentally, you're trying to pull out what are the most important components of this chunk of data, of this matrix. Yeah, they're very related, and there's going to be a homework problem where you're going to exactly work out exactly how these are related. So it's coming for you.
Be able to generalize that for images that are more structured, that the rank is lower for those images? Is that how that works, or can it be different based on like the different patterns you see in the images?
It could be different, but I think fundamentally images that it does depend. I mean, it depends on how they're similar. In this case, if you just have repeating ones and zeros, rows of ones and zeros, in this case, the rank of that matrix is lower. So that is, your observation is correct. Yeah. Okay, good. So I'm going to move on. So we're going to prove this theorem, and we're going to prove it over 2 lectures, today's lecture and tomorrow's lecture. It's quite an involved theorem. And one of the reasons that I really like doing this proof in class is because it pulls together so many different ideas from linear algebra that we've been building out so far. And I really like that it shows kind of the power of the tools that we've been developing. And one of the things that I want you to take away from this proof is not necessarily that I expect you to memorize all the steps of this proof. And I promise you there will never be a question on the exam that says prove the Eckart-Young-Mirsky theorem. So, don't copy the entire proof onto your cheat sheet. I mean, you're welcome to if you want to, but it's not going to. Understanding the steps. And what I want you to get from this is like how you can think about things as interconnected. How can we take kind of a complex, this for many of you might be the most complex proof that you've done in the class so far. Okay? So that's one of the reasons that I want to what I want you to see is the process of the proof more so than the memorization or the details of the proof, though it's hard to understand the process without the details. The other thing is that this proof is often, there's like a very easy way to do this proof completely wrongly. It's a false proof, and it's repeated in many, many sources if you look online. And the other thing that I will hopefully, by the end of tomorrow's lecture, I'll be able to get to showing this wrong proof. And what I want you to get from this is also this lens of being critical and questioning and trusting yourself. And, if you don't understand something, it might be wrong. It might not be you, right? And, getting to the fundamentals and really thinking about something And that's why I like to emphasize fundamentals and this understanding in my classes, because I want you all to feel confident in thinking about something and like asking questions if you don't understand it. You know, it's good to ask questions. It's good to think about things critically. Okay, so keep this in mind as we're going through this proof. So we're going to do the 2 norm first, the spectral norm, and then we're going to move to the Frobenius norm. Okay. So we want to prove that the argmin of this thing is AK, right? So what is AK again? Let me write out AK here. So what is the rank of AK? It's a K-rank matrix, right? Good. And if I now consider, so I'm looking at this spectral norm of A minus B, and I want to prove that the best one is AK. So if I consider A minus AK, what is this equal to? So A I know is a summation like this. A is this summation going from 1 to R. AK is going from K to R. So A minus AK is a summation going from K plus 1 to R, sigma I, Ui, Vi transpose, right? So how many non-zero singular values? This is also a matrix, right? Inside this 2 norm is a matrix. And how many non-zero singular values does it have, this matrix? R minus K plus 1, right? Okay, good. Can you actually compute the 2 norm of this matrix? What is the 2 norm of this matrix? Remember, what is the definition of the 2 norm?
Sigma K plus 1.
The 2 norm of a matrix is always the largest singular value of that matrix, right? So what are the singular values of this matrix? Sigma K plus 1, sigma K plus 2, sigma K plus 3, all the way up to sigma R. What is the largest singular value of this? Sigma K plus 1. Right? So here we were saying that the argmin is AK. And if that is the argmin, what will be the min? What is the minimizing value? Sigma K plus 1, right? When you plug in AK, what you're getting is sigma K plus 1. Make sense to everyone? So now if I wanted to prove my theorem, right? Remember, when we're proving these kinds of bounds, we've done this technique now a few times. I find something that's my best guess of what the optimizer is. And then I say, nothing can be better, right? So I've kind of gotten my choice. So now what I need to prove that AK is truly the answer is I need to prove nothing else is better, right? We've done this now technique a few times in class. So that means what I need to show is that for any B, and what is the restriction on B? Is it any B? For any B of rank K, right? This is important. Because maybe if I could choose more rank, I can do better. Right? My main restriction is that this is of rank K, and AK is restricted to rank K. Or maybe it can be less than or equal to K technically. A minus B 2 norm must be greater than or equal to K, right? This is what I need to show. Yes, everyone with me? Yes?
So are you saying the argmin of that is?
No.
Or the value?
The value of this thing. The argmin is a matrix of this thing. I'm not even writing a min here. I'm saying for every B that is of rank K. There's not a minimization problem here at all. Okay? Is everyone with me on what we're trying to prove? Because if you lose me here, then like, bye-bye rest of lecture. Yes, question?
Can you repeat what we're trying to prove?
We're trying to show that for any b that is of rank k, right? So take that optimization problem over there. We want to show that the argument is ak. So that means what we want to show is we choose any b that is not ak, we have to do worse than ak does. Right? So ak we know gives us the value sigma k plus 1. We want to show any other b does worse. Everyone with me? Okay, good. So this quantity now, what kind of thing is this? What kind of norm is it? It's a matrix norm. Do we like matrix norms? I mean, maybe we do, kind of we do. But if you had a choice between a vector norm and a matrix norm, which one would you choose? Vector norm, easier to deal with, right? Is there a way to convert this matrix norm into a vector norm? Right? Can we write this matrix norm as a vector norm? What is the definition of matrix norm? This is basically a maximization over a bunch of vector norms, right? So if I was to think about this matrix norm A minus B 2 norm, and I want to compare it to A minus B times some W 2 norm, where W is now some unit vector. Okay? The 2 norm of A minus B matrix is basically the largest value that this thing can take, right? So can you write an inequality between this? Can this ever be strictly bigger than this? This must always be the left hand, I guess on yours, I don't know left and right, but the matrix norm must always be greater than or equal to the vector norm, right? Because by definition, this is saying choose, like, maximize this quantity. Yes, everyone with me? So if I want to prove that this thing is larger than sigma k plus 1, instead, if I try to prove this is larger than sigma k plus 1, is that good enough? Right? And it's easier to deal with the vector norm, so I'm going to deal with the vector norm instead. Make sense to everyone? We're together? Step by step, we're basically trying to make things, let's make it easier, let's make it easier, let's make it easier, is kind of our general life approach. Okay. So now, let's look at this thing. Now you wanted to say, let's say you wanted to choose W in some way. Of the two things here, of A and B, which one do you know more about? A, right? B is some arbitrary matrix. All we know is that B is rank K. For A, we have its full SVD sitting with us, right? We basically know A perfectly. We know nothing about B. So what's the thing? If you could get rid of something from this expression, what would you want to get rid of? B, right? So you're multiplying B by some vector. What's the way to get rid of the B? Remember, we get to choose this W, right? This inequality holds for which W's? How many W's does it hold for? For all of the W's, right? There's infinitely many unit vector W's that this holds for. So we're going to want to pick our best W, right? We're going to strategically pick the W to get us to this sigma k plus 1, right? So if I could add, to my wish list on W, what would I want to be true for W? Someone else? Yeah? Null space of B. If W is in the null space of B, brilliant, right? Great way to send things to 0. Okay, so let's just say Can we choose W? No one says no. There's unit vectors in the null space of B. So, and what do we know about B? B is rank K, right? And so it's embedded in a larger dimensional space. K, we're saying, is strictly less than M and N. So B has a null space, right? It's not that the null space of B is just the 0 vector. Because if we chose W to be the 0 vector, that would not be interesting, right? Then this whole thing would just be 0. So we want to have a non-trivial vector in the null space of B. Okay? So choose W. We want it to be a unit vector anyway. And the null space of B is non-trivial because K is less than M and N. Right, to achieve any kind of compression, we want to necessarily have K be smaller than R, which is smaller than M and N. Okay, good. So if we have this now, if we have this property, then I have A minus B times W, 2 norm, is equal to AW minus 0, 2 norm, right? Just given that we've chosen W to be in the null space of B. Okay? So now we want to think about this AW. And now here we get to the, starting to think about the SVD. W is some arbitrary vector, but if we want to think about how it interacts with A, what is the basis that it might be convenient to think of W in? I can equivalently write this, right? Just substituting the SVD of A. So what might be a convenient basis to consider W in? If I could write W in the V basis, so I could write it as V times some vector alpha. That's very convenient for me for understanding how A acts on W, right? Now what's coming down to is thinking about how does A impact W. So when in doubt, think about the SVD basis is often a good thing to think about, right? Because it makes it easy to understand how a matrix is changing a vector when it operates on it. So if I was to think about this, I could have these V's very nicely cancel, right? And I could understand more easily how W is being scaled by A, which is basically what the heart of the 2 norm is getting at, right? How is W being scaled by A? And if I can get rid of this rotation by V, that's very helpful. Yes, question?
How do we know that V alpha or W in this case still lies in the null space of?
Ah, good, good, good. Someone's paying attention. The question is, wait, you just chose something in the null space of B. Now you're saying, looking at it as other basis. How do you know that something's going to exist here? You can't just say, give me a unicorn and then my problem is solved, right? You have to prove that the unicorn exists. And so, exactly, we have to prove that this unicorn exists, right? We're finding properties of W that we want. So, one thing to note is that V is an orthonormal matrix, right? So V is just a basis representation of Rn. So I can always write any vector in the V basis, but we are going to have to find and prove that a W that satisfies all of our desires actually exists, okay? So we have to figure out exactly what this alpha is that we're going to choose such that we can ensure that the vector is still going to be in the null space of this matrix B. Okay? So let me write out V as V1, V2, VK, VK plus 1, all the way up to Vn. Okay, this is my V matrix. And now I want to consider a specific, right, let me write this further as kind of Vk plus 1, and then V, I don't know what, k plus 1 to n. Or maybe I'll just write Vk plus 1, Vk plus 2. Okay, so I'm taking these like first k plus 1 guys and calling them Vk plus 1. Yes? So okay, the question is, we know that W is in the null space of B. And why can't I just say, okay, choose some W in the null space of B. We know some such vector exists. And then just say that, well, now take that vector in the null space of B and express it in the V basis. Absolutely, that's one thing we can do, right? So if we take an arbitrary vector in the null space of B and express it in the V basis, so what will we get? We will get U sigma V transpose, and let's say I have now V times alpha. Okay? I don't know yet what alpha is, but say, I can always write W as V times alpha. V is an invertible matrix, so nothing prevents me from writing it this way. This is equal to U sigma. What does V transpose V give me? Identity. So this is just U sigma alpha, right? So now I want to basically try to understand what's going to happen to this 2 norm. Everyone with me? What makes it easy for me to try and understand this interaction here? So sigma is conveniently has many, many zeros in it, right? So sigma times alpha is, in a sense, easy to compute. What do I want this thing to be equal to? What's my desired thing? Sigma k plus 1, right? And sigma k plus 1 is this is now, so I want this thing to be equal to sigma k plus 1. So I want to somehow pull out this sigma k plus 1, right? If I look at this, what is this? This is U times, what if I just sigma times alpha, what is this thing? This is some vector. This is U. What is U? U is an orthonormal matrix. This is the 2 norm of this thing, so doesn't change, right? So what can I further write this as? Right? So now all that remains is to choose the appropriate alpha. And I'm worried I'm going to run over time. Yeah. So how exactly are we going to do this? So I'll give you a quick version now, or do you want to think about it and do it next class? Quick version? Okay. How many people want the quick version? How many people want to think about it and do it next class? Second one wins. Sorry, overwhelming. Okay. See you next class.